All right, we now turn our attention to capacitors. A capacitor is a device used in electric circuits. We've talked about how it's similar to a battery. However, it's more appropriate for short-term energy storage, electrical energy storage that is released in short, quick bursts. And this is because of a potential difference or a voltage that is shared that goes across the conductors of a capacitor, and the static electric field develops that stored energy, and then a force happens between those two. So as we've seen in the simulations, we see that a typical parallel plate capacitor would look something like this, and it would have a positively charged plate and a negatively charged plate, and in between those two plates there would be an electric field that is shared between the two of them. Now this is what the inside of it looks like. The outside, so this would be the inside. The outside of it looked like what we've shown you before, right? A nice little cylinder or something like that. So that's what you're seeing is the inside, and this is what it actually looks like in real life. Okay, so inside of it we have parallel plates. So what we have then for problem 2, this is what it typically looks like, right? We have two plates. Here we have a positively charged plate, we have a negatively charged plate. And what's happening is that the electric fields go from positive to negative. Now what's happening is that in between this sandwich is what we call a dielectric. So this right here, this yellow region, we call this a dielectric. And what the dielectric is an insulating material, which helps with the electric field and with the energy storage. Okay. In our class, we're not going to really focus on different dielectric materials. They can vary from capacitor to capacitor. We're going to simplify things in this class, and we're going to refer to what we call free space or air as our dielectric in this class. We give you an equation now for capacitance. C, capacitance, is the charge over the potential difference. Q is a magnitude charge. And delta V, of course, is the potential difference or the voltage, which has units of volt. C has a unit of F, which is also read as farad. I know we've used F in some cases you've used F in the past, degrees Fahrenheit. We never really did use Fahrenheit in this class, and if it were to be used, you should not confuse it because that has the symbol of degree, and in our case, we don't have that symbol. Problem 3, we have a 3.0 microfarad capacitor. That's microfarad, micro being 10 to the negative 6. It's connected to a 12-volt battery. What is the magnitude of the charge? So magnitude again means absolute value. It means don't worry if it's positive or negative. Just worry, because we didn't tell you what end of the terminal it's connected to, right? If it's connected to the positive or to the negative terminal of the battery. So just worry about absolute value in this case and the magnitude of the charge on each plate of the capacitor, because we know that one plate will be positively charged and one will be negatively charged. So if we go ahead and solve this for Q, we get this set up. And that gives us, the coulomb is 3.0 times 10 to the negative 6. Sorry, this should be, yeah. This is the capacitance, I'm sorry, this is the capacitance, farads. It gets confusing with the C's everywhere, right? This C is not coulomb, this C is capacitance, and then the V is voltage. And so we get in the calculator 3.6 times 10 to the negative 5 coulombs, or it might be more appropriate to write this as 0.36 microcoulombs, okay? Be careful with the units and the symbols here, right? C does not represent coulombs over here. This C represents capacitance. This C at the end represents coulombs, which is the appropriate unit for charge, which has a symbol of Q. You're going to want to, at some point soon, refresh your table to show all the symbols and the units and how they relate. Summary: what would more or less potential difference increase capacitance? Would more or less potential difference Increase capacitance. Explain. Another formula for capacitance, this time is not in terms of the electrical capabilities, but of the geometry of the capacitor, so how we design it, okay? A is the area, okay, which will be in meters squared, and D in this case will be the distance of separation between the plates. That'll be in meters, okay? E, or actually it's not an E, this is the Greek letter epsilon. This is a lowercase epsilon. Epsilon is another constant. It's 8.85 times 10 to the negative 12 coulomb squared over Newton meter squared. These units are going to be pretty helpful in canceling things out. This ends up being our dielectric. Remember how I told you earlier how we're not going to have the material or anything. We're going to keep it simple, and free space or air, the gap between the two plates, in this case will be just filled with air, and that's what we're going to use this number for. Okay? Now, just to give you an example of how this formula would work, let's say we have, we're given this area right here with this plate separation. We would find this number by doing the capacitance by using the formula up here. And so we would do, the 8.85 times 10 to the negative 12 coulomb square, Newton meter square. And then we would multiply that by the area. And then divide that by the distance between them. And it's millimeters, so I'm going to make it into meters. You'll notice, for example, that the meter squares cancel out. Okay, and you can do some fancy stuff with the newtons and the coulombs, and you'll get the capacitance. But if we put this in a calculator, we're going to get 9.75 times 10 to the negative 13 farads for this example right here. And if you go ahead and if you recognize that a picofarad is 10 to the negative 12, then that would go ahead and end up giving us a, that's going to be 0.875, typo. That should be a 0.975, 0.975 picofarads. You might want to I think one of the most difficult things besides using a calculator with this topic is going to be recognizing your units and your prefixes, right? Your micros and your picos and your nanos and your millis. So you might want to print out a table or pull up the table that you used last semester for this kind of stuff. Okay, problem 4. We have a 10 nanofarad capacitor. Nanofarad, which would mean 10 to the negative 9. And we have a magnitude charge of 50 microcoulombs. So Q is 50 microcoulombs, not millicoulombs, micro. That's 50 times 10 to the negative 6 coulombs. And we want the potential difference. Potential difference is the voltage. So that's going to be C is equal to Q over delta V. We're looking for delta V. That's going to be 50 times 10 to the negative 6 coulombs divided by 10 times 10 to the negative 9 farads. And that's going to give me 5,000 volts. Or we could rewrite this as 5 kilovolts by using a calculator. Circuit diagrams. These are quite fun. We're not going to get into them as much in this lecture note. I wanted to begin to introduce you to some of the components of it. We will go a lot deeper into this on the next topic. So for a battery, right, a voltage, a potential difference, the symbol for this is going to look something like this, with a plus and a minus sign. I could also write it like this. Some diagrams do have them like this. Okay, and then a capacitor will look like this, or like this. Notice how they both have some similarities, right? For example, if we look at this one and this one, notice that they're parallel lines, but you'll notice that with a battery, there's one bigger than the other one. This is appropriate because we do know that capacitors act like a battery, but they're not as powerful as a battery, of course, and they serve in different ways. But it's very appropriate that we notice that the symbol for a capacitor and a battery are very much they very much look alike. So what would this look like in a circuit? So for example, if we start off with a battery, and then we have a capacitor over here, this would be a circuit diagram with one battery and one capacitor. Okay. We could also write this, for example, like this if we want.
I just cannot believe this.
We could even draw it like this if we want. Well, let's go this way instead.
I just cannot believe this.
The idea is that you have a battery, you have a capacitor, and then you have the wire that goes all around and closes the circuit. Great. What factors can affect capacitance?